Right, good morning everyone. My name is Dan Talman, and today I'm going to talk to you about the inner secrets of compilers. Now, a lot of the compiler talks I've been through in the past talk about lexical analysis, grammars, recursive descent parsers, pattern matching, machine code generation, all of the fundamental parts of compilers, but which frankly are a little bit boring. So I'm going to talk about the inner secrets of compilers, some of the things they do in modern optimizing compilers that make them generate really nice code, which are actually very clever. And nobody really tells you about. So first of all, who am I? So I'm a toolchain engineer. So I work on compilers, debuggers, assemblers, linkers, simulators, and so on. And I do that for massively multi-core systems. So we have several hundred cores per chip. We can connect several of these chips together and create several thousand cores in a single system. And so for the last 14 years, I've been developing toolchains for supporting those sorts of systems. I'm an official GCC fork maintainer. Been involved with GCC for about 10 years now. Attend lots of their conferences, very interesting. I'm technical lead for a multi-core debugger. Again, for massively parallel systems, making a debugger that handles that is a lot of fun. And at the moment, I'm a system architect for a telecoms company. So that's who I am. What am I going to talk about today? So I'm going to give you a very brief anatomy of a compiler, just to set the scene, so we know what we're talking about, we know how everything fits together, that I'm going to talk about later on. And then I'm going to spend roughly 5 minutes on these 4 topics. So I'm going to talk about register allocation, vectorisation, which is increasingly important in today's multi-core world, induction variables, and debugging optimized code. So the compiler does some really clever things here, but how do you actually debug the code that is generated? I'll have a little look at that. So, the anatomy of a compiler. It's made of 3 major components. The front end, which takes the source input, the back end, which does the machine code generation, and the wonderfully named middle end. So the source input takes one of these languages, and any more that you wish to add there, and it converts it into something called intermediate representation. Now, intermediate representation is effectively it's like an assembly language, but it's very, very generic, so it's not targeted at any particular platform, any particular processor. It's very high level and applicable to lots of different languages. So the front end takes a source input and it converts it into intermediate representation, and then this iterates. It does lots of things inside here, going round and round, and each time it takes a representation of the program and it does a conversion to create another representation, which is hopefully smaller or faster, or as is often happening in today's world of embedded devices, uses less power. You can actually compile things so they use instructions which are less power than another instruction. That's a very interesting branch of compiling that's happening at the moment. So it does a sequence of source code intermediate representation optimizations there, and eventually it gets to the back end where it takes that generic assembly language and converts it into a particular target language. So if you're running something like GCC and you run it without optimization, what effectively happens, it takes this, it bypasses all of this, and it goes straight to that, so it doesn't really do any optimization at all. If you turn on optimization, various things start to happen here. So everything happens in the middle end, and that's where I'm going to be concentrating today. So, register allocation. So you've written a program, and you've got lots of variables in that program, and now you're mapping it onto your target processor, and the target processor has a finite number of registers. It could be 8, 16, 128, even 1024 in some cases, so that's a bit excessive. So the compiler has to take those variables and map them onto a register. How does it do this? A digression. Map of Europe. You can see all the borders and the seas and so on, but we've not coloured it in, completely blank. And what I want to do is colour this in so that every country is given a different colour to its neighbours. This is called the map making problem. And I'll give you bonus marks if you can answer these questions as well. So if you had n colours, could you colour the map in? What is the minimum number of colours you need to colour it in? And if I gave you n colours and said, yes, you can colour it, how would you actually go about doing it? They're all the same question, they're just rephrased in different ways. So, let's formalise it. We'll create a graph. So for every country, we'll create a node, and if 2 countries share a land border, we'll put an edge between them. and we end up with something like that. I've missed out lots of countries, I got bored after. And once we have this graph, we can use a special algorithm called a k-colouring algorithm. And the idea of a k-colouring algorithm is you give it a set of k colours, so you might have 10, and the algorithm applies those colours to the graph such that two nodes connected by an edge do not get given the same colour. This is an NP-complete problem, so I'm not going to show you how to do it now. I've only got another 25 minutes. So you just have to trust me that such algorithms exist. So there's the solution. There's one solution. As you can see, no two countries with a land border have the same colour. And the bonus mark, so what is the minimum number of colours? Well, for a two-dimensional planar graph like this, it's 4 colours. Next question, if you had n colours, could the map be coloured? Well, from my previous answer, 4 colours, yes. 4 or more, yes, you can do it. 3, maybe, I've not tried, I don't know, probably not. Leave that as an exercise for you to do later. So, what's this got to do with register application? Here's a little program. This is intermediate representation, so it looks a bit like a assembly language. Don't look too closely because it's not real, it's made up. And what we do is we create things called live ranges. Now, the idea of a live range is the first time you write a value to a variable, that variable becomes live. And the last time you use the value in that variable, the variable becomes dead. So the point between those 2 points, the range between those 2 points is called the live range. So here we have a few live ranges. So we have a variable up here that we write to, and we use it somewhere down here, can't see where. And so we say the live range of that variable is the entire program. And we can do this for every variable in the program. We create these separate live ranges, which shows when they're actually holding useful values. And what we do is we create a graph for each live range. So, and now we go through this program line by line, and on each line we look across and we see what live ranges are live at that point. And if 2 live ranges are live at the same time, we create a line, an edge between the nodes here, like so. So we can see that this point here, V1 and V4 are both live at this point, so we put an edge between them. By the same reckoning, if we've got V4 here, V3 here, they're not live at the same point, and so there is no edge between them. So now we have a graph, and we can apply a k-colouring algorithm of registers to that graph to perform our register application. So now we can see that V1, which is live for the whole program, has been assigned to register 1, and register 1 is not used anywhere else in the program. So we've achieved our register application. But I say k-colouring was NP complete. So how can compilers do this in reasonable time? Well, compilers are extremely optimistic, so they're going to assume that it's going to work. And this isn't unreasonable. If you've got a machine with 128 registers, that's not unreasonable to assume it's just going to work. If you've only got 8, not such a good assumption. So they just proceed along the lines that it's going to work. If it works, brilliant, done. If it doesn't, you can change the problem. Let's go back to our example here. We've got a big live range, but the variable is written to here, used here, and nowhere in between does anything else use it. So what we'll do is we'll split the live range. So at the start of the program, we'll write that variable into memory, and then just before we need it down here, we'll read it back from memory and use it. So we've now split this big live range into 2 small live ranges, and that makes the graph coding problem easier. Smaller live ranges, less interference, more chance of register application working, and you just keep on doing this iteration. Try it, did it work? No, it didn't. Fix it. Try it again, did it work? Yes, it did. Fine, we're carrying on from there. And that's how register application works. Okay. All right. Vectorisation. Okay. When you're operating on large data sets, you're doing the same thing on all of the elements of that data set. And what vectorisation allows you to do is parallelise those operations. But how does it do that? Firstly, what are vectors? So a vector, rather than like a, it's just a collection of related bits of information, related data. So here we have a vector, it's a single location, but it has 8 items of data within it. two types of operation to it. The first operation is called a vertical operation, or a mapping operation. So we have a register vector here, A, we have another vector B, and if we do an add to create a vector C, all we're doing is we're taking elements pairwise from these, so we take these two, add them, and create that one. These two, add them, create that one. These two, add them, create that one. So that's a vertical operation, also called a map. We can also do a horizontal operation. So we have our vector here, and we've got 8 elements in it, and we reduce it to one element, a scalar element. So a max is a good example. So just take all of those values and find the maximum value and write it into here. That's called a horizontal or a reduce operation. So vectorisation is important for many different types of large data set processing. Vector units, to exploit this, are everywhere. They're also called SIMD units, which stands for single instruction multiple data, but it's just vector. So Intel MMX and SSE 1, 2, 3, 4, and AFX, or whatever the latest one is. PowerPC, which is in your Xbox, has it. GPU engines are vector engines, and they're doing lots of things to pixels at the same time. The ARM7, which is in your iPhone or your Galaxy, has a vector engine. They're everywhere, so it's very, very important that we can somehow exploit this. Vector algorithms are not just important for microprocessors either. They're used in larger arenas. You may have come across the term MapReduce. Google make a big thing about it for processing their data. It's just another name for vector operations, just a different type of way of applying it. I tend to use horizontal versus vertical because that's what processor people use, but MapReduce is equivalent. So, to show you how to vectorize a program, I'm going to take this little program here, and what it's doing, it's trying to find the maximum element from an array. So we have an array of 916 elements, and each time through we just say, is it bigger, and take the maximum, like so. And what I want to do is show you how to vectorize that. So the first problem, I said 916 elements. That's not a multiple of 8, which is what I'm assuming from my vector unit. So we've got some remainder elements. They're a problem. We can't process those at the same time. So the first thing we have to do is take that 916 array and split it and do two things. So first of all, we start by processing 912 elements, because that's a nice multiple of 8, and then we clean up and do the remaining 4 there. This bit, I'm just going to forget about. There's nothing really we can do to make that any more efficient.
You could zero pad.
You could zero pad in some cases. It depends on the type of algorithm you're using. So if you're trying to find a maximum, zero padding would be okay. If you're trying to do some other operation, it might not be applicable. So yes, you're absolutely right. That is one way of doing it. This is a more conventional way of doing it, but take it. You need to have domain knowledge if you're going to zero pad, which you don't need it.
Cool. I do have here the domain knowledge I use on cross line.
Sorry?
The domain knowledge you use on cross line initialized to 0.
Oh, okay. Yeah. Fair enough. Okay, the next thing we do, now we've got our nice multiple of 8, is we do something called strip mining. And what this is doing is taking your array and blocking it off into separate little loops, each of the right vector size. So we have an outer loop, which iterates over the array in blocks of 8, and we have an inner loop, which processes those 8 elements. Let's make it a little bit more like assembly language. So I've expanded up here, so still we have our loop here. There's our inner loop, and this time what we're saying is, first of all, we have to do a load operation. We need to read the value of that array element into our register, and then we do the max operation. So these are two, basically they map to assembly instructions. But we're trying to create vector instructions, so we can't do two things at once. So what we need to do now is take those two separate instructions and put them in loops of their own, so that we've kind of squashed it down. So we've taken those two loops and we split them into two separate loops, so loop distribution, so that this looks more like a vector instruction now. So it's doing a single operation 8 times and a single operation 8 times. And then it's quite straightforward to just convert those two loops into a vector load and a vector max instruction. So what we've done now, the overall effect of this vectorization is to take a loop which runs over single elements at a time, and now it's converted it into a bigger loop, which is taking them 8 elements at a time and just doing 2 instructions per loop, and that's much faster. And then you can take this and you can do further optimisations to it as well, but I'm not going to cover that. As I say, we could do strength reduction and induction, which I'm going to talk about in a moment. We could do loop unrolling, do software pipelining, modular scheduling, and a whole bunch of other things. Induction variables. So many loops contain values which are related to each other. And if you understand how they're related to each other, you can improve the code generation by taking advantage of it. So, here we have a simple source program. It has an array, and we just initialize it here. So each element is initialized to I times 5. So first element 0, 5, 10, 15, 20, and so on. And this is intermediate code to represent that. So this is what would be generated by the front end, so the source language to intermediate representation conversion. So it's quite verbose. And if you compiled this particular loop with GCC with O0, so no optimization, you get something which looked pretty much like that. But there's lots of inefficiencies in it. We have the variable I, which is counting from 0 to n. That's a loop index. Here we have this temporary, which is storing the value of I times 5, and that's incrementing in steps of 5. Here we have the address calculation, so that's working out where to write the value into memory. So it's doing it's counting from the start of the array to the end of the array in blocks of 4 bytes. So we've got 3 different ways of counting the loop, but we don't really need 3 ways. We only need 1 way of counting the loop, ideally, and that's what we're going to try and achieve. And it also contains two multiplications, and multiplications tend to be expensive, and you tend to want to avoid them. I know that that's actually multiplied by 5, so it's a shift, but bear with me. So if we look at the values written to each element, I times 5, each time through it increments by 5, so it's assigned 0, 5, 10, 15. So what we can do is, rather than do a multiply each time we go through a loop, we can start off by assigning 0 to the temporary at the beginning, and then each time through we just add. And that's called strength reduction. And in this case, I've done it for the value being written, but here we can also do it for the address. So each time through, we're calculating the address to which we're writing that value, and each time through, we can just add 4, because that's the number of bytes in the word that we're writing to. So what we've done is we've changed the multipliers into adds, and adds are much cheaper instructions, and it also opens up the opportunity for doing instruction level parallelism. So if you have 2 multipliers, most processors only have 1 multiplier unit, so you'd have to do 1 multiplier followed by the other. If you have 2 adds, well, most processors these days have multiple addition units, so you could do both adds at the same time. So it will be much faster. Okay, what else can we do? Induction. So we have 3 different additions now. I, the loop index, is incremented by 1 each time. T0, the value we're writing to the array, is incremented by 5, and T2, the address, is incremented by 4. Now the only reason that I is in there is to count the loop. So at the start we initialize it to 0, we do a comparison with the end of the loop here, and we increment it here. That's the only reason that I exists. But we have 2 other ranges. We have T0 iterating over that range, and we have T2 iterating over that range, so we could use those to index a loop instead. So what we've done here, we've taken I, and we've changed it. So now we create a new variable here, which is the end of the loop. So we're saying n times 5, the end of the loop that we're getting to. And we change our initial comparison to just compare the value we're writing to the end of the loop. There we go. We've now changed to loop indexing. So we can eliminate those 3 instructions and replace them by 2. But more importantly, we have eliminated 2 instructions inside the loop and replaced it by 1 instruction inside the loop. So that's saving us. Can we do better? What else could we do to that? What else is wrong with that?
unroll the loop, or you can check the end instead of the start.
So unroll the loop, yes, you could do that. That's more complicated than I want to talk about today. What, your second suggestion?
Check the condition at the end, because it's never going to be true if the box down lamp.
Okay. So indirectly, I think the branches are the problem here. So we have two branches. We have a branch here, which is your comparison, and you have a loop closing branch here. So we have two branches, and branches are expensive. You really don't want to do branches. So how could we eliminate the branches? How could we get fewer branches? Well, this branch here, the loop closing branch, is always required. So how about we take this comparison branch and move it here? And then we end up with one branch on there. But how do we do that? Let's think back in source terms. What we can do, in the original program, it's a for loop, which is actually a while loop in disguise. And we can change it into a do-while loop. Now, a while loop has a condition it checks at the start. Now, a do-while has a condition at the end. And so it also acts as a loop closer. So what we can do is we can put the condition down the end like so. But we need to look out for what happens if we only had 0 iterations. In which case, this would execute, get to here, and oh, shouldn't have done that. So we wrap it inside a little condition here, and we say, if n is greater than 0, then we'll do the branch, and we'll put the loop closure at the end. Now, I've shown you that in source terms language, but actually it would happen in intermediate code.
You're missing a race in that second.
I didn't compile it. Okay, I missed the race. So here we go. So we've taken this comparison and this loop closer, and we've done comparison up here with 0. And then if it is 0, we immediately skip past the entire loop. Otherwise, we go into the loop, we do our instructions, then we do a comparison at the end, and this is your loop closure as well. So now we've taken 2 branches and we've replaced it by 1 branch. So we're doing pretty well there. We've only got 4 instructions inside that loop. And in the original program that I showed you, the unoptimized program, that had 9 instructions, so we halved it. And we had 2 branches in that, so that makes it expensive. And we have 1 branch, so we're doing really well. And just to show that I haven't been making all this up, this is the output from GCC, generated for x86. So if we have a quick look, here we have our test against 0. This is comparing them the same against itself. Branch down here, we have a bit of loop set up here. Here we have adds, which are doing the strength reduction. Here we have comparison at the end. Okay, so that's what we get. Okay, 5 minutes left. So as a little aside, what do these do? Have you come across them? They're idioms in C. If you haven't used C, then maybe you don't know this one.
String copies and
Fixed length and 0 terminated string copies.
Memcopy and string copy. Actually, it's not memcopy. I've deliberately introduced a typo. That's in the wrong place. That was deliberate. Because most people go, oh, well, that's a memcopy. No, it isn't. You just think it is. I still see this coming up on Stack Overflow, for example. What's the fastest way to copy a string? Do that. That's really quick. It's got pointer dereferencing. It's got assignment inside a loop condition. It's got pre-imposed increment. It's going to be really quick, isn't it?
Maybe that's the shortest source code.
That's going to be really, really quick. No, it isn't. If you do that, which is dead obvious, the compiler will produce code which is faster than that in most cases, because it uses strength reduction, it uses induction, it uses all of these techniques I've just showed you to do something really, really clever. If you give it that, a lot of the time what will happen is the compiler will look at it and go, oh, the program is really advanced. I'm not going to touch it. I'm just going to generate really boring code. When you're writing code, it's a very good idea to write the simplest, cleanest, noddiest code you can find, because the compiler will be really good at recognizing it and doing a good job. As soon as you start doing clever things with it and trying to fool the compiler, you've lost it.
although control was if you're using GCC, at least if you actually call memcopy and star copy, it's small enough to inline.
I've got a slide about that later.
Oh, excellent.
Yes, if I have time. Okay, so this is all very clever. We've got a compiler producing really, really good code, but how does the debugger make sense of it? As Kernighan said, debugging is twice as hard as writing the code, in the first place. So if you write it as cleverly as possible to begin with, you won't be able to debug it unless it's your compiler as well. Some of the really clever things that compiler does to debugging, it can't understand it. But we can get close. We use a language mostly called dwarf, which is debugged with arbitrary record format. In a rather kinky fashion, the dwarf is stored inside an elf. And the arbitrary record format bit means that you can extend it. So if a compiler wants to support a particular platform and clever features, the dwarf can be extended arbitrarily. And very importantly, it's non-intrusive. That means that the code does not change when you enable debug. There's still some compiler vendors, even these days, who use a different form of debug information called cough. You enable debug, your program changes, and the bug disappears. Really, really helpful. I won't just name and shame, but I'd love to. Okay,
Microsoft.
Variable location. I'll talk about one aspect of dwarf, which is variable location. So where does a variable live? So here's a few expressions which show where a variable might live. So it might live in a register, it might live in a constant memory location, it might live in a memory location which is indexed by a particular register. It might be a constant. At the start of your function you might say int I equals 0, and until you use it, that variable has a constant expression. It can be multi-part, so we could say the first 16 bits are stored in this register, and the remainder is stored in memory. That's called scalar replacement. Now the clever thing is that the debugger contains a virtual machine. It's a stack-based virtual machine, so rather like a Java engine. And the variable expressions are simply instructions to that virtual machine. So suppose we have a function, we pass it a parameter, and that parameter is on the stack. How do we tell the debugger where that variable is? We can use a little program like this, and here's my stack engine inside the debugger. So the first instruction, register stack pointer. So we take whatever the stack pointer is at the moment and push that value onto the stack. We then take a constant offset, so the location on the stack where that variable is, which in this case is 12, push that onto the stack. We do an addition, pop the two values off, add them together and push the result back on. And then, so that's the memory location. We then do a dereferencing operation. We get 42, which is the answer to everything. And hey presto, that is the variable value. That's how the debugger, how the compiler can tell the debugger where that variable lives. This is really useful, this programmability. If we think about our induction optimized loop, we had a variable I, but we got rid of it. We optimized it away. But the debugger can still generate that value I, because it knows what the two other indexes were that were used to control the loop. So we could take the temporary that we've created, so that's going 0, 5, 10, 15, 20, and so on. So we take that value, push it onto the stack, push the value 5, do a division, and hey presto, we create our variable I. So even though I doesn't have a physical existence, we can still work out what it is and present that to the user. So the virtual machine has full implementation of the processor, does arithmetic, memory operations, branching, can do all sorts of clever things. It's got some extensions, and it allows the compiler to tell the debugger what it's done to your program, so that the debugger can reverse engineer all of the clever optimizations that have happened. It also means that the compiler can generate special data types. So if you had a linked list, for example, there's no built-in support for linked lists in most debuggers, but the compiler can generate a sequence of programs for handling linked lists. And then any debugger which is capable of using dwarf can use those linked lists and give you the output of what they actually store. So there we go, 11 o'clock. Hopefully I've revealed a little bit about some of the clever things that compilers can do, and some of the things that they basically let you write some very sophisticated algorithms which you can write clean, understandable, testable, maintainable code, and let the compiler deal with all the nasty complexity. Are there any questions? You did have a comment earlier, if I'm allowed 30 seconds. What is the fastest way to move or copy a block of memory? Any suggestions?
At what level?
At the source level. At C. If you're writing a C program and you want to move an array from one place to another, it's the fastest way. The reason is, if the length is no, and you've hash included std.lib, the compiler is allowed to generate code to do that directly. If a compiler can't do that, because it doesn't know the bounds or whatever, it will call into a runtime library. The runtime library would have been heavily optimized to make it really fast. The runtime library will know about the presence of vector units, it will know about the cache sizes, and it will choose the right way of blocking that memory. If it's a really big bit of memory and the runtime library doesn't like the look of it very much, it will hand it off to the operating system, which can do memory moves, it can do page, all sorts of clever things with the organisation of processor and actually do stuff under the hood. So, all you need to do is mem move, and all of this knowledge